Welcome back. Lecture 33 today. We were not in the middle of a problem. We were actually in the latter stages of a problem where we were trying to find absolute max-min and or relative max-min. So let's go back to that problem, and that should finish us up from that, unless you have any specific questions, either clarification type questions or WebAssign questions you want to ask before we start section 4.3. We have time to do that. I think we have time to do that today. So we were doing this problem as class ended yesterday, searching for absolute and relative max and min values. It is over a closed interval from 0 to 2 pi, and it is a continuous function. So we should have an absolute max and an absolute min. We haven't determined those yet. We have some candidates. How did we do this? We started with finding the endpoints. You don't have to start with that, but at some point in time that should be part of the problem. So plug in 0 into the function and see what you get. We got 0. Plug in 2 pi into the function, see what you get, and we got 2 pi. So those are possible highest and lowest points, whether they are they're not going to be relative max and mins, but they might be absolute max and mins. The second part is to take the derivative and set it equal to 0. We already did that. So the derivative of this function, 1 minus 2, derivative of sine of x is cosine of x. We set that equal to 0. This was right at the end of class yesterday. Cosine of x is equal to half. We don't want all values, but we do want the values from 0 to 2 pi. And as class ended, we got those two values, pi over 3 and 5 pi over 3. Keeping in mind that that's the two quadrants where the cosine is positive. First quadrant, reference angle pi over 3. Fourth quadrant, reference angle, again pi over 3. That would be 5 pi over 3 to get us there. Now, what we didn't do is plot these points. So let's pick up with that. We do know that these are critical values for x, pi over 3 and 5 pi over 3, but we need to know what points to plot, so we always go back to the original function. I guess I should at least address it. We don't need to find here where the derivative is undefined. Why not? Would this derivative ever be undefined from 0 to 2 pi? No. Never would be. So we could write that down. That's the other kind of critical points, finding where the derivative is undefined, but it's kind of a waste of ink and space and time to do that on this problem. There aren't any of those kind of critical points. So we need the f of pi over 3. We'll probably have to do a decimal approximation. So the function is x minus 2 sine of x. So that'd be pi over 3 minus 2 sine of pi over 3. What is the exact value for the sine of pi over 3? The equivalent of the sine of 60 degrees. Square root of 3 over 2. And we are doubling that, so this 2 and that 2 will knock each other out. So the exact value is pi over 3 minus the square root of 3, but we probably want a decimal equivalent. So we know where to actually plot that point, which is part of what we want to do to finish this problem. What is the number pi divided by 3, which is, what is pi divided by 3? 1.04 something, minus the square root of 3, which is larger than that, so we should get a negative number.
Negative 0.6848.
6848, getting a consensus?
Yep.
So the point was pi over 3, the x value. The corresponding y value is approximately that. So that's what, one of our critical points. And visually, what should happen? What should be happening at that point?
Flat. Should be flat.
Should be flat. That's correct. So at that place, the derivative is 0, so it has a horizontal tangent line there. So a way of taking care of that is just describe it as that's a flat place. We also need the f of 5 pi over 3. So that is back into the original function, x, which is 5 pi over 3 minus 2 sine of x. Sine of 5 pi over 3. Now it's the equivalent of the sine of 300. We're in the fourth quadrant, and the sine is negative. And negative square root of 3 over 2. So we've got minus and negative, which will be back to positive. These 2's reduce. So again, we're finding a point where the slope of the tangent is 0. That's how we found this point. That's how we found the x value. And what is a good approximation for the y value? 6.968. Thank you. 968. And again, what's happening there? The graph is instantaneously flat at that point. So we found the endpoints, did that yesterday. We'll plot those. And we know this is a continuous function, so we have to be able to, without any breaks or open circles or vertical asymptotes, we have to be able to connect all points as we move from left to right. And now we have the critical points. Here's a critical point, and here's another critical point. That should be it, right? If we wanted a sketch of this, and if we want, well, we don't need a sketch of it. These are candidates for absolute min and absolute max. Do they win the contest? The contest for the absolute highest value and the absolute lowest value.
Are you talking about these over here?
Oh, might help if I put them actually where you can see them. Sorry. These values, thank you, 0 and 2 pi were endpoints. So this is possibly the lowest value. Is it the lowest value? No, we got a lower value right here. This is possibly the highest value. 2 pi is what, 6.28? Did we do better than that?
Yeah.
Okay, we actually did better than that over here. Okay, so although they were candidates, and I'm sure we're all tired of hearing from candidates at this point in time, these particular, hey, both of them lost. How about that? I kind of like the sound of that. Maybe we could like vote them both out. I could think of some replacements that might work better.
No, I don't know that.
All right, so let's get a picture of this. Of course, you don't know what race I was talking about. I could be talking about the mayor of Apex, right? That we wanted to get rid of both candidates.
Sure.
That's what I'm talking about, actually.
Or even.
I thought you were talking about math.
0, 0. I know where that is. That's an endpoint. Over 2 pi and up 2 pi. That point is also an endpoint. So we want to be able to connect things from here. The critical points. Pi over 3. So 2 pi is about 6.28. Now we're going to plug in the critical points, the places where it's instantaneously flat. Pi over 3 is what? Where are we? 1.04, a little more than 1. So if that's 6, a little more than 1, let's estimate is right here. And at pi over 3, we will go down negative 0.68. I'll call that right here. And what is happening there? We know the graph is flat. Little reminder that it's nearly flat coming in and nearly flat going out. The next critical point is 5 pi over 3. What's a good decimal equivalent for that? 5 times. So 5.1?
5.23.
5.2? All right, so if that's 6.2, let's put that right here. 5 pi over 3, and we go up to 6.9, so almost 7, so above this point. And what's happening on the graph at that point? It is instantaneously flat. Now, we have to be able to connect all the dots. So from this endpoint, what do? We have to decrease, right? We could do some other tests to validate this, but I don't think there's any confusion that it has to decrease and flatten out as it comes in here. How do we get from this critical point to this critical point?
Going up.
It's got to increase. How do you get from down to up? The only way you get from down to up is to increase. So it leaves here fairly flat, and it enters here fairly flat. And how do we get from this critical point to this endpoint?
Decrease.
It's got to decrease. It's got to leave here fairly flat. Now, that's kind of rough. It's a generality of what it does, but you should be able to, as we did with the points, pick off the absolute max and min. This is the absolute min. And remember, it's the minimum value of the function. So the absolute min is what? Negative 0.6848. That's the lowest y value that we'll plot. The absolute maximum value of the function is approximately 6.968. And we also have some relative max and mins. This is a relative min, right?
Mm-hmm.
Because in an open interval containing pi over 3, so a little bit left and a little bit right, that is the lowest point. So a relative minimum occurs at the point pi over 3 negative 0.6848. And a relative max, which happened to be the absolute max as well, occurs at this point because if you take an open interval containing 5 pi over 3, it is the highest point in that open interval.
So when you're doing relative, you do points, and when you're doing absolute, you do values?
I think technically it's the y value that you really talk about in both of them.
Okay.
But there's nothing wrong with given points, but you can't just give an x value because that's not really, that doesn't answer either one, relative or absolute. But I like to kind of describe where the relative min happens. It happens at a point. But when you ask for the absolute min, we're kind of asking for the lowest y value. But really, we're interested in y values here for the most part.
Okay.
That's probably not a very good answer, but when in doubt, put the y value is the best thing to do. Now, does that look like what you think this function should look like? There's our original function.
Yeah.
Does it have properties of y equals x? Do you see y equals x in there in any fashion? I do, because this curve oscillates much like a sine function, but instead of oscillating on the x-axis, it oscillates on the line y equals x. So sine graph does this kind of thing, right? But that's not a sine graph. It's actually negative 2 sine of x. Do you see negative 2 sine of x and how our graph has features of that as well?
Yes.
So it oscillates on the line y equals x, and it does have features of minus 2 sine of x because minus 2 sine of x would start down, right? Work its way back up, cut the axis, not the x-axis this time, the x equals y line, and then do its positive bit and come back here. So it does, in essence, have properties of both of those, y equals x and y equals minus 2 sine of x. Questions on any part of that before we leave that? In the directions we were given yesterday, make sure we answered what, excuse me, I think we said we were searching for absolute max and min, is what we set out to do on that problem yesterday.
I actually have a WebAssign question.
Okay? And if we don't have any more questions on that, then this would be a good time for that. Any further question on this problem? By the way, I wouldn't call this what I came up with here. I would call this a sketch. It's not accurate enough to be a graph. I would need to know that point. It's just not good enough to be a graph. But it's a pretty good general idea of what this function does on the interval 0 to 2 pi. Anything else before we go to a WebAssign question? All right, go ahead, Chandler.
Okay, it's asking for the critical numbers of the function f of z equal.
I don't like that already. I don't like z's.
Do you want
Go
to do
ahead.
x then? I mean, it doesn't matter. Oh. Z, I hate writing them. Z
Okay.
plus 1 over z squared plus z plus 1.
No.
And what do they want?
They want the critical points of z.
Okay.
Or critical numbers, I guess.
Critical numbers. So
Yeah.
that's different. Critical
Oh, okay.
numbers means you can give just the x
Z.
values,
Yeah,
right?
that's what I was asking.
Okay, and critical points means you actually find the x values, throw them back
Then the
into the
y.
function, and give the y values.
Just the
So we want
numbers.
critical numbers.
Yes.
Okay, and I've got that written correctly. And that's the same problem for everybody? Everybody had the same exact problem. What problem number?
Number 7.
Okay. All have a general idea of what to do. What would you do?
Derivative.
Okay, find the derivative. So we have a quotient. So denominator times derivative of numerator minus numerator times derivative of denominator,
2z plus
2z plus 1, all over the original denominator square. Does that look right?
Yep.
Yes.
Okay. Kent, you're stubborn. So we distribute the 1. That was really difficult. And then we subtract everything that follows. Need to keep track of the signs. So we're going to subtract what? 2z squared.
Yep.
We're going to subtract 2z and then another z. So subtract 3z.
Yeah.
And then
Minus
subtract 1. Obviously, we can combine some terms in the numerator. Do we lose any terms? 1 minus 1. Those knock out.
Negative z squared minus 2 squared.
Okay, we have a 1z squared and a negative 2z squared, so the net result is negative 1 or negative z squared. So we took care of that and that. Negative 3z plus 1z minus 2z. We might want to factor the numerator. Factor out a negative z. And that leaves us with what?
X or z minus
Z plus 2.
plus.
All right, so we have the derivative. Now we want critical numbers. We need to do what with the derivative?
Set it equal to 0.
Okay, one of them is to set derivative equal to 0. So we want negative z, z plus 2. So we have a fraction. When is a fraction equal to 0? When the numerator is equal to 0. So we want negative z times z plus 2 equals 0. And when does that occur? When z is 0 and
Negative 2.
z is negative 2. So if they want critical numbers, We have two of them. Let's continue because we do have a fraction. We don't normally have that, but this problem we have a fraction. So we did find where the derivative was 0 by setting the numerator equal to 0. We also need to see where the derivative is undefined. That's another kind of critical point. Those aren't flat places. What can we call these? A cusp or a corner, or we could, I guess we're given kind of this one word description. The graph is pretty steep there. It gets steeper as it approaches that point. At that point, it is about as steep as it can get because it's vertical. And then if it leaves there, if it actually is a point, then it leaves there fairly steep as well. So a different kind of point. These kind of points graphically, I usually, instead of putting a little flat line, I'll put one of these, and I know the graph gets steeper as it comes in, and it leaves there fairly steep. So that's just one of the possibilities. But that's a typical vertical tangent line. So our derivative is that, and we want to know where it's undefined. How do you see where a fraction is undefined?
Denominator equal to 0.
Where the denominator is 0. So we've got the same factor twice in the denominator, so we'll just take it. So is that factor that is squared in the denominator, could it ever be 0? Is that factor?
Yes.
Doesn't factor, so we could use the quadratic formula. It always solves for the variable that's being squared, which in this case is z. And that would look like -1 plus or minus square root of b squared, which would be 1 squared minus 4. Not looking good, is it? Times a times c. I'm not going to finish that. We don't need to finish that. Why not?
Because it can't be negative.
Okay, because we have a negative under the radical, and we're dealing with real numbers. It's got to be able to be graphed on the xy plane, which is a cross product of the reals with the reals. So we're not going to find any solutions this way. No critical numbers this way because that is negative. Negative number under the radical is imaginary, so we'll scrap that. No solutions, no critical numbers from that. Is that all right?
Mm-hmm.
Any other WebAssign questions? Experts, that's what I like, a bunch of experts. Means I'm not really needed very much.
This was the first website that
Yeah,
we
that was
were
the easiest
discussing
one.
it.
Oh,
the
that was
first
easy.
Yeah.
See, I always do the easiest ones, right? Whether I do them myself or you pick them out for me. That's my goal in life anyway, is to do the easiest ones, leave all the hard ones for you guys. All right, anything else before we go on into 4.3? All right, let's do that. This has to do with not necessarily just the high points and the low points. Those are important. And you can make a pretty good sketch if that's all you know, endpoints and high points and low points. This has to do with everything else, increasing, decreasing, concave up, and concave down. So this is kind of shapes of graphs from the standpoint of increasing, decreasing. We already know the flat part. We set the derivative equal to 0, and also concave up and concave down. So kind of how the graph proceeds. And concavity might be kind of a subtle change. There's nothing subtle at all about increasing and decreasing. I mean, it's headed up or it's headed down. That's not subtle. How it heads up, it could be concave up. It could be increasing like this, which is concave up. It could also be increasing and concave down. So both of those are increasing, but they're kind of subtle changes in how it's increasing. All right, before we get to that, the author takes up with what is called the mean value theorem. So let's take that on initially, and then we can spend the rest of the time with why it's increasing, how do we determine that, same thing with decreasing, and why is it concave up and down, and how do we determine that. First thing is the mean value theorem. Let me draw a picture of it first. So we have a function that is differentiable, and I'll put that all the kind of stipulations up here in a second. So it has a derivative. We can find its derivative from some starting point, from some a, f of a, to some other point, b, f of b. So we've got 2 points on this curve, which is differentiable everywhere, all the way from A to B. So we know it starts here, and I put it below the other one. I could have put it above it. I could have put them at the same horizontal position. So there's nothing, I mean, it's just kind of random the way I drew it. So could we determine the slope of the secant if we know where a function starts and we know where it stops? The answer is yes, because the secant line is just this dotted line that goes from a f of a to b f of b. So there's our 2 points. If we wanted the slope of the line segment that connected them, we could find that. So I'll call it the slope of the secant is f of b minus f of a all over b minus a. Difference of the y's over difference of the x's. If you want to call that slope of the secant, that's fine. It's also kind of the average change as you go from this point to this point. We don't know exactly how we get there, but we do know we start at the first point and we end at the second point, so that's the average rate of change, or I'll just refer to it as slope of the secant. Let's say the curve does something like, this is pretty simplistic picture, and we'll make it less simplistic on the next diagram. But the curve increases and increases fairly rapidly, and then the rate of increase kind of tapers off. So somehow I have to connect this point to this point without a corner, because it's got to be differentiable. No asymptotes, no vertical asymptotes, no open circles, and no corners in order to be differentiable. So this theorem says that with all these things in place, there is some value c. I don't know exactly where that is, but I know I can picture it up here, where the slope of the tangent is exactly the same as the slope of the secant. So the slope of the tangent, let me try to figure out where that is. Maybe it's here, where the slope of the tangent line and the slope of the secant line are exactly the same. So if I make them parallel, their slopes are the same, right? So this value is, they refer to in the theorem as c. So the slope of the tangent at c, first derivative at c, that's what it is equal to the slope of the secant the theorem guarantees that there's at least one value, where that is true. Now there might be more than that, but in this case there's only one. There's only one c value where the slope of the tangent line is exactly the same as the slope of the secant that connected the two endpoints. So there is the mean value theorem. So this is in your book, so you don't need to copy this. Questions on this before I move it? So this is what your book says, mean value theorem. F is a differentiable function. That means the derivative exists. No vertical asymptotes, no holes in the graph, no corners. So it's differentiable on the whole thing, from A, including A, all the way to B, including B. It's got to be differentiable everywhere. Then there exists a number. Actually, there exists at least one number. So A typically means 1, but in some cases there are actually more than one. But there's at least one number, C, between A and B, such that the slope of the tangent is equal to the slope of the secant. So that's kind of the original statement of the mean value theorem. If you multiply both sides by B minus A, you get this version. I choose to remember this version because I just have to remember slope of the tangent equals slope of the secant, and then I can generate the equation from that point. So that's in your book. It does have to be differentiable. On this sheet, since I have a little bit of room, what if it's not differentiable? Well, then there is not a C that's guaranteed. So let's take our first point and our second point and connect them in such a way that the function is not differentiable. Something like that. Everybody agreed? Derivative doesn't exist right here. So here's the slope of the secant. Can you visualize any point along this curve where the slope of the tangent is the same as the slope of the secant? I can't either. In fact, it's not guaranteed, and in fact, it doesn't exist here. So if it's not differentiable, then there is not a C value that's guaranteed. And in like fashion, if it's not differentiable, starting point, ending point, let's say there is a vertical asymptote here, so the curve does something like this. In any case, it's not differentiable from A all the way to B. It's not, the derivative doesn't exist where the vertical asymptote is. Can you visualize any point on the two branches of this curve where the slope of the tangent would be the same as this? And in fact, there isn't one. There doesn't have to be one. The reason, because it's not differentiable. So this little word here, not that it's a little word, but the fact that it's included is important. The curve has to be differentiable in order to guarantee at least one of these numbers C. There might be more than one. So again, our starting point is here, our ending point is here. Let's say the curve does something like this. We've seen that happen. Here's the slope of the secant. There's the secant line. Can you visualize a point, or in this case, more than one point, where the slope of the tangent is exactly the same as the slope of this dotted line? Somewhere in here, the slope of the tangent is the same as this dotted slope of this dotted blue line. Somewhere, I don't know, right here, the slope of the tangent. So this would be a C1. That's one of our C values. This would be a C2. So the theorem guarantees one, and in this case, more than one. So at least one. So here's our A value, and here's our B. And there could be more than two. There could be lots of them depending on how much the curve actually oscillates. So the F prime at C1 is equal to F of B minus F of A all over B minus A. And the F prime at C2 is also the same as the slope of the secant. If you're driving your car without stopping from Raleigh to Charlotte and your average speed is, you do it too much? Sorry, bring up a bad memory there. And your average speed is, you want to stay within the law. Let's say it's 63 miles an hour. Okay, you're a law-abiding citizen.
We get there fast.
If your average speed is 63 miles an hour and you drove continuously from Raleigh to Charlotte or Charlotte to Raleigh, did you ever go exactly 63 miles an hour on that trip?
Probably.
Yes, you
Yeah.
did. This theorem guarantees it, right? If your average speed is 63 and you did not stop and start, in other words, you've got this continuous driving pattern from Charlotte to Raleigh or Raleigh to Charlotte, did you ever actually go 63 miles an hour?
Yes.
Guaranteed you went 63 miles an hour at least once during that trip. Never thought of it working that way, did you? Give you something to think about driving from Raleigh to Charlotte. All right, increasing and decreasing. Let's take issue with that in the time that remains. Probably won't get concavity. You don't need to copy this down. This is in your book. And you probably already know this. So this kind of validates something that at this point in time in this course, I hope you've at least thought about a couple times. And now it kind of gives us permission to use this stuff. What determines if a graph increases or decreases? Well, we can not just based on the picture look at where it's headed up or where it's headed down. We can look at the derivative. If the derivative is positive, then it's increasing on that interval. That's not anything new, right? Everybody knew that? You gonna be able to stay with us, Katie? Okay. You with us? And now, why is that true? Not true because James Stewart, who wrote this book, says it's true. I mean, you
Because-
ought to be able to justify that.
Because all the slopes of the tangent lines are
They are
Positive.
positive,
yeah.
right? What is a first derivative? It's a slope of a tangent, and if the slopes of the tangents are positive, right, that means that curve is headed up. That's the only way it could be. And if the slopes of the tangents are negative, that curve is on its way down as you read the graph from left to right. So that's nothing new. We've used that some, but not a lot to this point in time. Okay, putting a couple things together that we've had. This isn't really completely new either. If the derivative changes from positive, meaning the curve is doing what? Increasing, and the derivative is now negative, and that occurred at a certain point. If it's increasing and then all of a sudden changes to decreasing, what kind of point is that? It's a local or relative max. I mean, think about that. Increasing to decreasing. It's got to be a local max. If it changes from negative to positive, negative means it was decreasing. Now all of a sudden it's increasing. That must be a local min. No new information there. We haven't dealt a whole lot with this. A lot of times we'll always change sign of the derivative, where it changes from positive to negative or negative to positive. Sometimes it doesn't change at all. So what would it look like? Positive, then kind of instantaneously flat, and then positive again. That's possible. So we've got this point where the derivative is 0, and it's increasing into there and increasing out of there. Is that point a relative max or a relative min?
No.
It's neither one, because you have to be able to look at an open interval containing that point. Is it the highest point in that open interval? No. Is it the lowest point in that open interval? No. So it's not a relative max nor a min.
And the sign, and the f of x does not go from positive to negative. It stays positive on one side and positive on the other.
That's
or
right.
negative on.
Right.
Okay.
So if it were negative, then flat, and then negative again, so here's our flat place, decreasing, nearly flat, and then it is flat, leaves here fairly flat. Same thing there. That's not a relative max, not a relative min. So let's take this example. Of course, you know we always start with the easy examples. I'm going to take the easy ones and leave the hard ones to you. This one actually isn't all that easy. But it is a polynomial, so that's fairly kind. So a fourth degree polynomial. How many turns or changes in direction can a fourth degree polynomial have?
4.
4 changes in direction? It can have 4 solutions or roots, right? So let's just see, this isn't this graph, but any fourth degree polynomial could cross the axis 4 times, right? 4 roots. The degree of the polynomial, same as the roots. So if it is a polynomial and is continuous, it could look something like this. So if I were to connect those 4 roots or solutions, how many possible changes in direction would do that? 3. So it could have 1 less than the degree of the polynomial. That number, minus 1, changes in direction. Is that true? How about a quadratic? Let's take it back into something that we worked with a lot. What is a quadratic? It's a parabola. How many changes in direction does a parabola have? 1, which is 1 less than this, right? Now, that's not to say that it's going to have that, okay? Because I can think of a cubic, a very simple cubic polynomial, that one, y equals x cubed. That looks like this, doesn't it?
Yeah.
So it doesn't have any, but if it did have some changes in direction, the most it could have would be 2. And if it did have roots or solutions, the most it could have would be 3. That's the problem. This only has 1 root, right? That's why it didn't change direction lots of times. All right, well, let's go back to this fourth degree. Let me rewrite it since I cluttered that up. So if we want to determine where it's increasing and where it's decreasing, we need to use the derivative, which is what?
12x cubed minus 12x 72.
And that's it, right? Derivative of 1 is 0. And typically, we want to find the critical points first, and then use those critical points to determine where it's increasing and decreasing.
Okay.
So we want to take that derivative and set it equal to 0. So critical points, most specifically critical numbers for x, if we want to determine where it's increasing and decreasing. So let's take this thing and set it equal to 0. What would help?
Pull out an x.
12, take out a 12x, okay? And if we do that, that leaves us with
X squared minus x minus
minus 6. And let's factor that if possible. Minus 3 plus 2.
yes.
All right, so we're searching for critical numbers for x. So what are the x values that cause the first derivative to be 0?
0, 3,
0, 3, and negative 2. So if we wanted to plot them, we would go off to the side and find the f of 0, the f of 3, and the f of negative 2, okay, to find the actual critical points. And we know what's happening there. Because the derivative is 0, we know that these are flat places. Now, this is the part that we haven't done yet, so this part will be new. I think we'll just have time today to do this. I'm going to do and you don't have to do it exactly this way. This is kind of my habit to do this chart in this fashion. You can choose your own little version if you don't like this one. Just don't tell me about it, hurt my feelings. So we find the critical numbers. 0 is one of them, negative 2 is one of them, and 3. And don't worry about, is everything spaced out correctly. These are the 3 critical numbers, and I'm going to see if I can determine what the function does by what the sign, SIGN sign, of the derivative is in that region. So I want to check this region from negative infinity to negative 2. not including negative 2 because I know what it does at negative 2, between negative 2 and 0, between 0 and 3, and then to the right of 3. And it doesn't matter what number you choose. It's just called a test value, any number in that region. These are the only places where it's going to change. So that's why it doesn't matter what number you choose, because whatever you find it to be positive, it's positive for every number in that interval. So let's see what the derivative is at, just pick a number in here, negative 3. You can pick any other number if you want to. And we don't need the numerical value. All we need is the sign. So I usually try to pick the factored form. So if I put in negative 3, 12 times negative 3 is negative. Negative 3 minus 3 is negative. And negative 3 plus 2 is negative. So did we have 3 negatives, right? What's the product of 3 negatives? Is negative. So that means the function itself is doing what there? Decreasing. If the derivative is negative, the function is decreasing. And keep doing that same thing. From negative 2 to 0, negative 1 is in there. 12 times negative 1 is negative. Negative 1 minus 3 is negative. Negative 1 plus 2 is positive. Negative, negative, positive. The product is positive. So that means the function itself is increasing. Sorry, it's getting a little cluttered down there. Number between 0 and 3.
2.
Doesn't matter. 2. Kent says 2. I always do what he tells me to do. 12 times 2, positive. 2 minus 3, negative. 2 plus 2, positive. So product is negative.
Yep.
So the function is decreasing. And any number to the right of 3.
Positive.
12 times 4 is positive. 4 minus 3 is positive. 4 plus 2 is positive. The product of 3 positives is positive. So the function must be increasing there. Is that okay?
Yep.
And that's all we can determine there. Now, some things that once we plot points, because it went from decreasing to increasing, what kind of point are we dealing with here?
The local min.
Decreasing to increasing. Local min, right?
Yeah.
Here we went from increasing to decreasing, so that's a potential max. It's at least a relative max, and so on, right? So this is our first derivative chart, and we'll continue with this example, but that's the bulk of what I wanted us to see today. We will meet tomorrow. Joyfully.